Okay, in this lecture we're going to continue with the complexification averaging method. We stopped at equation 54 where we had circled this term in blue, and so this was a complex conjugate of the uncircled term. So one thing that we corrected after the last video off screen or off recording was that this component that I'm circling was divided by 2, and that was missing at the end of the last video. So from here, we can then write this down as being phi dot over 2 plus j omega over 2 phi plus c over 2 phi minus 3j alpha over 8 omega cubed phi squared phi bar minus k over 2j, that whole quantity multiplied by e to the j omega t plus j alpha over 8 omega cubed phi cubed e to 3j omega t plus cc is equal to 0, and here we've lumped all of those terms that were circled in blue into the term cc. From here, we're now going to apply averaging. Now, I know we didn't cover this in the class, so we're just going to apply it here, and we'll skip all of the theorems that go behind this and just simply apply it. And this you'll do every time you apply the CXA method, you will end up doing averaging in the same kind of way. So I'm just going to copy this equation down right here, and I'll paste it over here. So when we do averaging, we are just going to eliminate all of the components that have fast frequencies that are higher than omega. And so in this case, we are just going to throw away this last term right here. We're just going to eliminate it and ignore it. And that is what happens when you do this averaging. And then as a result of that, what we'll end up finding is that phi dot over 2 plus j omega over 2 phi plus c over 2 phi minus 3 j alpha over 8 omega cubed phi squared phi over bar minus k over 2j. This is then equal to 0. And that is our slow flow equation, or we can prove over the term that doesn't have phi in it, and then we'll get phi dot over 2 plus c plus j omega over 2 phi minus 3j alpha over 8 omega cubed times phi squared phi over bar is equal to k over 2j. And this is our slow flow dynamics. So assuming that k is constant, then the steady state response is computed by setting phi dot equal to 0, which then results in the following: that c over 2 phi plus j times the quantity omega over 2 phi minus 3 alpha over 8 omega cubed times phi squared phi over bar, and then that is equal to k over 2j. From here, we are going to expand phi in a polar representation such that phi is equal to a e to the jb, and then phi bar is equal to a e to the minus jb. And substituting this expression in, what we end up with is c over 2 times a e to the jb plus j times the quantity omega over 2 times a e to the jb minus 3 alpha over 8 omega cubed a cubed times e to the 2jb times e to the minus jb. And that is all equal to k over 2j. We can eliminate the 2 up here and then eliminate that exponential term. And then from here, what we end up getting is that the quantity c over 2a plus j times omega over 2a minus 3 alpha over 8 omega cubed a cubed, all of that quantity times e to the jb is equal to the quantity k over 2j. And we're now going to pull out a e to the minus jb and an e to the jb, and we'll get here e to the minus jb multiplied by e to the jb, and in this case we can now eliminate e to the jb on both sides. And of course e to the minus jb multiplied by e to the jb is equal to 1, such that we're allowed to do this. So from here, we're going to convert the right-hand side into trig functions, and then we're going to separate the real and imaginary part, and doing so, we get the following. We'll get that c over 2a is equal to minus k over 2 times the sine of b. That's our first equation. And then the second one we'll get omega over 2a minus 3 alpha divided by 8 omega cubed times a cubed, and this is equal to minus k over 2 cosine b. From here we'll square both of these equations and add them together, resulting in the following. We'll have c squared over 4 plus the quantity omega over 2 minus 3 alpha over 8 omega cubed times a squared. That quantity squared, and everything in the square brackets multiplied by a squared. And then this is equal to k squared over 4. I'm just going to move this equation down. Expanding that square term, we end up with the following. We end up with that c squared plus omega squared over 4 minus 3, let me rewrite that, minus 3 alpha over 8 omega squared times a squared plus 9 alpha squared over 64 omega to the 6th times a to the 4th, all of that times a squared minus k squared over 4. That is then equal to 0. Okay, so we can compute the backbone branch for this system by setting c equal to 0 and k equal to 0. And by doing that, we will get that either a is equal to 0, but more interestingly, from the term inside the square brackets, we will end up with 9 alpha squared over 64 omega to the 6th times lowercase lambda squared minus 3 alpha over 8 omega squared lambda plus omega squared over 4. This is all equal to 0, and here lambda is equal to a squared. So from there we can solve for lambda, and lambda, well actually what we're going to do is we're going to divide by the leading term here, multiply by lambda squared, and by doing that we'll end up with lambda squared minus 8 omega to the 4th divided by 3 alpha times lambda plus 16 omega raised to the 8th power divided by 9 alpha squared, and that is equal to 0. From here, we can solve for lambda. We get that lambda is equal to 1/2 times 8 omega to the 4th divided by 3 alpha plus or minus the quantity. So we're squaring the middle term. 8 squared is 64. Omega to the 4th squared is omega to the 8th divided by 9 alpha squared, and then we're minusing 4 times that third term. 4 times 16 is 64, so minus 64 omega to the 8th over 9 alpha squared, all that raised to the 1/2 power. And what we find is that everything inside that square root actually cancels out. And then from here we can find that A, or the amplitude from the backbone branch, is actually going to be equal to, well, from here you'll find that lambda is equal to 4 omega to the 4th over 3 alpha. And since lambda is the square root of A, or lambda is A squared, we'll find that A then is the square root of lambda, and since A has to be positive, we will only consider the positive square root. So in that case, A ends up being equal to the square root of 4 omega to the 4th divided by 3 alpha. I'm just going to redraw my square root. And this is our backbone branch. Okay, so for the damped force response, we can solve for A or omega analytically, but the resulting formulas are very large, and they're just too large to provide and write down here. You can solve them using software like Mathematica, for example. And numerically, it's much easier to solve these by computing the roots of equation 62. That's why we wrote equation 62 here in this form, is so that we could actually solve for the roots. And that's what I've done on the next 3 pages for plotting the system. So here is an example where we are just varying the applied forcing amplitude. You can see in black dashed line is the backbone branch for this system. And as the forcing amplitude is increased, you can see that the response curves become larger and they progressively curve around this backbone branch. And you can see that there are regions where we again have 3 solutions. If we were to just draw a straight line through this, you'll find that there's a solution here, there's a solution here, and there's one here. So just like when we had weak nonlinearity, we again have 3 solutions here. One thing to note is that here we're plotting as a function of the frequency omega, the forcing frequency, not a function of the detuning frequency sigma. And in this case, the backbone branch still starts at 0. So we didn't have any linear generating term in the system, so the frequency will start from 0. If we have a linear generating term, then the frequency shown here will actually be able to, will start from that. So if we had some omega 0 squared term, our backbone branch would start from that value. And then also I'll add here that, we'll draw this in purple here, but the branch right down here, this is an unstable branch, and you can study the stability by looking at the equilibrium points of the slow flow equations that we found before. And the same thing here, this branch is unstable. And same with the blue, although I'm not going to draw it on the blue curve. All right, let's take a look at our next plot. Here, first of all, here is the code of how I did this. The code here is maybe a little bit advanced if you're not, if you're used to using MATLAB quite often. But I encourage you to take a look through this and see how I solved for these roots and how sometimes you get in general, there are 6 roots to that equation, 62, that we talked about up here. There are generally 6 roots. You can see that we would have a to the 6th power. In some portions of the curve, let me go back down to the curve. So in portions like over here, there's only 2 real roots, and one of them is negative, and since a has to be positive, there's only one root that satisfies our conditions. When you come to regions like right here, where I draw this line, there ends up being 3 roots that are real and positive there. And that's why we get these 3 different solutions. And then if we keep going, increasing omega, like right here, over here, there's again only one real root that is positive. All right, so here we're varying alpha, and so since the backbone branch here depends on alpha, you can see that as alpha is increased, we end up changing that backbone branch. In fact, the amplitude decreases as the frequency increases, and that tells us that if we think about, how does the frequency content change as the amplitude changes, a smaller amplitude is needed to change or create a larger change in the frequency content of the response as the nonlinearity gets stronger. If we were to plot this as in terms of a frequency versus amplitude, you would see that the nonlinearity acts as like a shifting mechanism in the sense that it shifts the curves to lower amplitude. So as you increase the strength of the nonlinearity, the amplitude or the frequency amplitude curve will shift to the left, meaning lower amplitudes is necessary to achieve a particular frequency. When we look at multi-degree of freedom, and particularly when we start looking at nonlinear normal modes, we will look at things called frequency energy plots, where we'll be able to show that increase in nonlinearity is equivalent to shifting the curves in the frequency energy plot. All right, on the next page we have what happens when you vary the damping. So as the damping is varied here, you can see that the backbone branch stays the same because it doesn't depend on damping, and the curves just bend around this backbone branch as well. And if you have enough damping in this kind of oscillator, you can actually eliminate these multiple solutions. In fact, this method breaks down when you have a damping of 1 in this case. In that case, it becomes critically damped, of course. Okay, we got a few more pages to go, and then we'll be done. So we can also solve the slow flow equations numerically to compute the slow amplitude. And so we're going to start off by rewriting equation 56. This was phi dot over 2 plus j omega over 2 times phi plus c over 2 phi minus 3 j alpha over 8 omega cubed phi squared phi over bar minus k over 2j. And then this is all equal to 0. So now what we're going to do is we're going to expand phi as a complex number. We're going to say use z1 and z2, and z2 being the imaginary part. And then, of course, our complex conjugate of phi bar, is going to be z1 minus jz2. We can substitute this into the equation above, and what we'll end up getting is the following. So we not only substitute, we also then expand it as well, and it results in the following. z1 dot over 2 plus cz1 over 2 minus omega z2 over 2 plus 3 alpha over 8 omega cubed times the quantity z1 squared z2 plus z2 cubed plus j times the quantity z2 dot over 2 plus cz z2 over 2 plus omega z1 over 2 minus 3 alpha over 8 omega cubed times quantity z1, z2 squared in this case, plus z1 cubed plus k over 2. All of that is then equal to 0. From here, we're going to separate real and imaginary terms, and we're going to end up recovering the following autonomous vector field. We'll have z1 dot is equal to minus 2 times the quantity c z1 over 2 minus omega z2 over 2 plus 3 alpha over 8 omega cubed times z1 squared z2 plus z2 cubed. That's our first equation. Our second equation is z2 dot is equal to minus 2 times the quantity c z2 over 2 plus omega z1 over 2 minus 3 alpha over 8 omega cubed times the quantity z1 z2 squared plus z1 cubed plus k over 2. So now that we have this autonomous vector field, we can actually integrate this numerically. There's a spelling error right here that I will fix. Numerically, and use that to compute the slow flow response. And that's exactly what I've done on the next page. So we can take a look at the code in a moment. But what I've done here is I've integrated numerically using ODE 45 this vector field 66 shown here. That's the red curve. And then I've also taken our equation of motion and I've simulated it using ODE 45 directly. And so you can see that the slow flow amplitude converges to the amplitude of that simulated or steady state response of that simulated displacement here. In this case, there is a transient response that dies out, and the slow flow does not capture that behavior. And so this is for a force amplitude of 1 and a frequency of 2. What did I change here? I changed the alpha. So you can see here alpha is equal to 3. If we decrease alpha, you can see here that again we're able to change that. If we decrease alpha to 1, here is a case where this approach actually fails. And then you can see from the simulated displacement there are clearly multiple fast frequencies that arise in that simulated displacement. And this is why the slow flow amplitude fails to capture that, because it's violating our fundamental assumption, which was that there was only a single fast frequency in the displacement. In this case, there are multiple fast frequencies. I think there's only 2 fast frequencies, but there might be more. But the point is that we're violating that assumption, and therefore the method breaks down. And the code for this is shown down here. In this case, let me zoom out a little bit. You can see how we have 2 ODE functions shown right here. This is the one for the slow flow, and then this is just the equation of motion. And here's how we integrate this and end up plotting that. Okay, that concludes our discussion of the method of complexification averaging, and it also concludes this chapter, or chapter 3 of our notes. From here, we're going to start looking at multi-degree of freedom systems. We'll do multiple scales we'll start with multiple scales from there, and look at internal resonances. We'll then try and study different types of nonlinear normal mode theories and see where that takes us from there.